I want to talk today about performance, durability and reliability of electric vehicles. So first of all, just a quick overview about who we at Prenscia are. So Prenscia is there to help engineers to deliver durable and reliable products, and hopefully to avoid the cost of those unexpected failures. And if you've heard about Prenscia, you've probably heard of us through the software brands. That's nCode and ReliaSoft. And between them, those brands, we deal with data analytics, which of course is the new word, which we used to call digital signal processing before. But we also deal with fatigue and durability in nCode and reliability engineering in ReliaSoft. As well as the software, though, we do offer training and education, and we do offer services too. So that rig that you can see there on the right, this is one of my favourite ones. This is a material testing rig where we're doing lots of work today on lightweighting of electric vehicles. So we'll come across that in a little bit. In terms of our products, as I say, we've got the ReliaSoft and nCode brands. So the first column here in ReliaSoft, these are all the reliability analysis tools that you'll see. So these handle statistical analysis, test planning, and system modeling. And in the second column, you'll find the reliability management tools. So these address risk management, maintenance, and corrective action planning. With the nCode brand, this is all about durability. So the third column along, these are our desktop analysis tools. So nCode Design Life is all about CAE analysis, and glyphworks is about test data analytics. And we've also got VibeSys for vibration and acoustic analysis. And then finally, that last column there on the right, Akira is our new software. This is our web portal for cloud integration. And of course, we've got automation, which is fleet-wide data analytics and test data management. So my interest in electric vehicles really started a couple of years ago when my boss, John Aldred, came to me and said, we've got a lot of customers who are using our software for designing electric vehicles. So I want you to ring them up, have a chat with them and find out what are they using the software for today, and what are the challenges that they have, and is there anything we can do to help them with that? So obviously I fit it into those three areas: performance, durability and reliability. I'd just like to spend a few minutes really just going through some of the things that we've found and the things we're working on to improve these areas. So if we just start off with that first area, the electrical and signal processing. So I want to talk a little bit about electric motor efficiency and loss mapping, and then about improving the accuracy by looking at better power measurement and analysis. And finally, by looking at how we actually work out what real-world usage is all about to get the best performance out of batteries in the real world. So we all know that the art of developing a good electric vehicle is it's all about maximizing its efficiency, because that leads to better battery range. We also know that when we convert energy from one form into another, then there's going to be an efficiency loss. And it's important for us to be able to measure that loss, to quantify it, and then to be able to minimize it. So we store energy as a DC battery, and then we pass that through a digital inverter, which converts it to AC to drive a motor, which then drives the transmission, which then drives the wheels and gives us kinetic energy. And what we're interested in doing is to look at the map, the efficiency map. So typically efficiency map is torque versus speed with the colour representing efficiency. And we want to maximize that efficiency range, the best efficiency we can, but also broaden it so that it works through all speed and all torque ranges as best we can. And the way we do that is by tweaking with the programming in the digital inverter and the motor to try and get the best efficiency in those areas. So this is the key area we want to look at. So in order to produce that efficiency map, we need to correctly calculate the power at each of these stages. Now, DC power is really easy, isn't it? Remember from high school that DC power is simply voltage times current. And mechanical power is easy too. It's just torque times speed. And even kinetic power, which we think may be difficult, is actually relatively simple to calculate. If we know the inertial, the gradient, the aerodynamic, and the rolling resistance, we can actually get a very good estimate of kinetic power based on the GPS signal. The one that's given me most trouble is actually the AC power. Now, when we talk to our cousins, the electrical engineers, then a lot of people have been working with the AC power grid. And in this case, we deal with a waveform, which is a three-phase sinusoidal voltage and current. And our cousins talk about active and reactive power. So active power is that's consumed by a resistive load. It's the stuff that turns on our lights, switches on the heating, and runs our production lines. It's the bit that does real work for us. But they also talk about reactive power. Now, reactive power is not real. It's actually when power goes back onto the grid, it goes back out of phase slightly. And that out of phaseness actually negates some of the power on the grid, and it can lead to grid instabilities. So our cousins working in the power line industry are interested in measuring active power because that's the one they want to charge us for. That's the one that's doing real work. But they want to charge us for the reactive power too, because that's doing damage. It's negating power on the grid and it can lead to instabilities. So they need to charge us for that. Now, if we look at the waveform coming from an electric vehicle, it's completely different. So we still call it alternating current. But in this case, what we've got is a multi-phase. So it doesn't have to be 3 phases. It could be 9 phases. It's non-sinusoidal. It's usually varying amplitude and varying frequency dynamically as well. So very different. But the engineers still talk about active and reactive power. So here, our active power is that's being consumed. It's the power that drives the vehicle, that turns the wheels, that does all the good stuff we want. And we talk about reactive power. Now, this isn't consumed, but it creates efficiency losses. And so therefore, we want to measure that as well. So we want to maximize the active power, the one that's doing his work, and we want to minimize the reactive power because that's the one that's building up efficiency losses. So as engineers, what we want is, first of all, an accurate measurement of active power, because that's the parameter we want to maximize. And we also want a robust inference of reactive power, because that's the parameter we want to minimize in order to build up our efficiency. Now, you might be wondering why I've used those two phrases. Why an accurate measurement of active power, but a robust inference of reactive power? And that's because active power is real. It's a real quantity. We can measure it, and we ought to measure it as accurately as we can. And that's the thing that's been driving our colleagues on eDrive to get the most accurate measurements that they can for power. But reactive power is not real. It's a mathematical construct. And so therefore, we want a robust inference. We want a mathematical parameter which is giving us a robust indication of reactive power, and we don't want it to change by noise in the maths or by changing wave profiles and things like that. We need it to be robust so that we can minimize it with confidence. So when we look at the profiles coming out of an electric vehicle, this is the current and voltage we see here. So nice sine wave of current, look, coming out of here. But the voltage is anything but sinusoidal. It's actually made up by pulse width modulations, look, of discrete amplitude. So it's not sinusoidal at all. And now if I multiply at each instant in time, the current and voltage, I find the instantaneous power. And of course, if I work the area out under this curve, I'm actually finding the energy. So a lot of this curve is positive. So the area under that is going to be positive energy. That's active power. It's doing work for us, driving wheels. We also find that there are negative powers in here as well. So the area under these are really making up the reactive powers. So hopefully we've got far more positive than we have negative. That's what we would hope. Now we can also take a PSD of these data as well. So here you can see on the top, this is the PSD here of current. So we're plotting the RMS level, if you like, with respect to frequency on the x-axis. And here's the voltage. And we can see that these profiles are really split into two. At the low frequency end, we see the fundamental frequency. That's the frequency of the sinusoidal AC current that's coming out. And then at the high frequency end here, over about 10,000 hertz, what we've got here are harmonics of the switching frequencies. The switching frequencies are these pulse width modulated. And if we have a look, we can see in that current signal at the top, there's about 4 orders of magnitude difference between the fundamental frequency amplitude and the switching harmonics. And that's why when we look at the signal, it looks largely sinusoidal, because although the switching harmonics are there, their amplitudes are very small. But if we now look at the voltage, then the amplitude of the fundamental is very similar, in the same range as the amplitude of the switching harmonics. And that's why we clearly can see those switching harmonics coming in here. They're a lot higher frequency, but they're of similar amplitude. And that's important. So what we're expecting to see here, of course, is lots of active power and a little bit of reactive power. Now, if we were to use the normal tools that we use for analysing the power on the grid, what we actually find is something peculiar happening. So if we look here, so my red now is the active power, my green is my reactive. This is showing that our EV drive is really quite inefficient, that the amount of reactive power is very high, higher in some places than the active power. And that didn't seem very realistic when we look back at this plot here, where most of it is positive and doing real work. So what's going wrong? Well, first of all, in the normal classical definition, we assume that power is purely sinusoidal. So we can look at this, and the active power is defined as the average of the voltage times current taken over a particular window size. And the window size has to be at least a half sinusoidal wave, or integer multiples of that. So we integrate it, if you like, to take the mean of the voltage times current over the half cycle and integers. And when we do that, that gives us the accurate power. And that's a very robust and it's a very accurate measurement. Now, if we assume they're purely sinusoidal, we can also calculate the apparent power. Now, this is taken as the product of the RMSs of voltage and current. However, we've not got a pure sinusoidal signal here. Remember that voltage with all of its pulse widths. So what's actually happened is we've overestimated the apparent power by quite a lot. And the reason for that is we've lost frequency content. We've munged all the frequencies together, and we're assuming that all of those high frequency harmonics are actually part of the fundamental frequency, which they're really not. And that's what's giving us a lot more reactive power here than we would expect. So thankfully, there is another definition, which is the broadband definition of power factors. So in this one, we keep the frequency content as well. So when we calculate now the active power is about the same as this. Sorry, I didn't quite get the axes on the same scale, but the active power is about the same. But now notice that the reactive power is much lower, far more robust, far more reliable, using the broadband definition. So that's the first thing. We need to use that broadband definition of the power in order that those power factors we calculate, the active and reactive power, are robust inferences. Otherwise, they will change with the shape of the waveform and the frequency that we're using. We don't want that to happen. So we've been doing a lot of work looking at the accuracy of these profiles. And one thing that's come out of it is when we do that work, we can actually go even further into detail. So these plots are always looking at the low frequency, so the fundamental. But what happens if you want to look at the high frequency end, the switching harmonics? So in this case, we've now got the high frequency power, and we're using the Hilbert transform, we can go in with what is effectively a digital microscope. So we can look at these little things in a microscope, and now we can calculate the active and reactive power at the really high frequency, at the hundreds of kilohertz range, the switching harmonics. And this allows us to look at the switching circuit itself to try and get better optimization of the power that's coming out. So a lot of work has been going on to try and get more accurate and robust calculations. So in summary then, our big thing here is looking at electric motor efficiency and loss mapping. So it's all about getting better vehicle range, calculating the efficiencies. Sorry about that. calculating the efficiencies with much better accuracy. And then we can plot that map, we can broaden it and stretch it and get a more efficient vehicle. And we make use of high-speed digital data acquisition, so the data coming from eDrive in order to do this. Now, accuracy is critical here, so we're now looking at electric inverters specifically, and we know that they're not sinusoidal, they're frequency modulated, they're transient, they're multi-phase. And what this means is that we get harmonic distortions, and we really want to understand that, because those harmonic distortions can lead to torque ripple, that can lead to structural vibration and efficiency losses as well. And we really want to understand these effects. And finally, we also want to understand what the real world customer's doing as well. How do people drive electric vehicles? What's the target customer going to be? Looking over the trends of how people drive over time as we get used to electric vehicles, but also over different world scenarios as well. And the idea is we're trying to build a better prognostic model that we can improve that real world reliability and maintenance and also maintain that battery state of health by looking at how customers use vehicles. So, of course, Glyphworks is really good at this. It's its bread and butter, really. So being able to take data from high frequency things like voltages and currents to low frequency, to CAN bus, to GPS, superimposing and working on all of those so that we can start to build a better picture and then do the statistical driver analysis and things from it. Okay, I could actually talk quite a lot longer on that, but Amy's going to shout at me if I do, so I better move on to the next section as well. So I now want to have a look at just 3 areas in the durability area. So in particular, I want to look at the fatigue design of battery packs, looking at accelerated testing of battery packs, and I also want to look at a more general case of vehicle lightweighting. So how do structures lighter so we can get better range out of electric vehicles? 2 years ago, when I started looking at this, I thought that the batteries were just electrochemical components and electrochemical engineers should deal with them. But then a customer corrected me. He said, actually, a battery is a hugely complex mechanical structure. At its heart, there's a collection of electrochemical cells. So they could be C shells, cells like this one, cylindrical cells, or they could be prismatic and things like that. But at the heart of it, it's a collection of cells. And these cells are joined together electrically by a bus bar, and they're also joined together structurally as well. Now, if we have a look at this, what we've actually got is a cell here, which is a mass with a spring damper system to it. So it's if you like, it's a dynamic system. And it's joined with these very flexible joints or connections to what is a flexible structure. So you can tell where I'm going with this. This is a relatively lowly damped spring mass damper system, coupled with the fact that there's about 5,000 to 6,000 of these cells per EV battery. That means that we've got between 10 and 12,000 joints per battery, each one being highly subjected to a vibration loading and vibration fatigue. So as my friend from the OEM said, these are not electrochemical systems. They're also hugely complex mechanical structures. And we, as automotive OEMs, we're the structures experts. And he was right. When we look at them, it's this big collection of vibration, but also thermally induced fatigue loading, especially at the joints. So this is the key thing that we wanted to look at to see if we could improve the reliability of batteries. You see, if one of these welds fail, it doesn't mean the battery's dead. But what it does mean is that that cell is no longer holding charge. So we get a progressive degradation. But more than that, what we find is as this cell weld breaks, that also reduces the stiffness. So there's a preference for the cells neighboring it to break as well. So we get this progressive failure. And that's what we want to try and avoid. So using some of our new equipment in the lab, for instance, we're really keen on trying to characterize these failures. So within Design Life, we've been able to characterize welds for some time. And now what we're working on is to look at the welds that are in electric vehicle batteries. So here we can see a specimen of a thin sheet material that we've had on test. We can see how the fatigue cracks started to grow and break. And if we look through you see where the primary cracks form through here as it's growing. And then as it started to grow, we can see a secondary crack forming here. Now, these materials, in order to test them in our rigs, are about 1.5 millimeters thick. So they're thin, but not as thin as a battery end tab, for instance. So this, when we do the test, gives us our parent material. But we're interested in what happens with the very thin materials. So what we're looking at now is how we can improve that to get this curve around here, because this is our weld curve that we can use in Design Life. So a lot of work going on at the moment to characterize these types of weld to make sure that we can accurately design them. After all, there's 12,000 of them in a battery, and we need to make sure that we've got the best design we can. But it's not just about understanding the materials and understanding the finite element and geometry. We also have to understand the loading too. And we do this using the very traditional approach that we've used in automotive. We first of all identify a customer, our target statistical customer. And then we produce a qualification test to give us the same damage, but in an accelerated period of time. And then we simulate the test. And hopefully this way we'll end up with a robust design. So where do we start? Well, I don't think it's fair to start with the same customer load as we were doing in the 1930s. But probably it is reasonable to start with the same vehicles as we used yesterday. So conventional sort of thermal engine vehicles is a good place to start for starting to work out what the loads are. What we then do, though, is we go to a proving ground. So by going from real target customers, what we're doing is we're now making that loading scientifically reproducible. So we can go out with confidence and measure the same sort of severity over and over again. Of course, not everything fails simultaneously. Proving ground, components fail at different rates, and it costs a lot to have drivers too. So we want to bring those tests into the lab. And so from the proving grounds, we derive accelerated qualification tests. And then typically, it's these tests that we want to simulate in our finite element analysis. And hopefully, by doing this process, if there's a failure at any point on this chain, we can use simulation to help us cure it. So if we find that it's failing in the sign-off test, we can go back to the simulation and know that we're simulating the test to work out why. Or if, heaven forbid, if an end user sees failure, we can look at the target customer analysis to make sure that we've got the right as being modeled. So this enables us to have this continuous improvement through simulation. Now, when it comes to batteries, what we've got, and we've had for a number of years actually in glyphworks, is the accelerated vibration test module. So we can actually go and we can measure the vibration that's going through the battery mount on our vehicles through the production line. This isn't just the structural vibrations from the roads. This is also things like the torque ripple effects and things like that at the higher frequencies. Now we've got those vibrations going into the battery. We can characterize those using the shock response spectrum and fatigue damage spectrum. These are a bit like PSDs. The shock response spectrum has shock on the y-axis and frequency on the x, and fatigue damage spectrum has fatigue damage on the y-axis and, again, frequency on the x. So what we find is the shock response spectrum hovers around a bit until we see a really big shock that's bigger than it's ever seen before. So usually with a car, it's things like potholes, curb strikes, things like that. And suddenly when it's more severe, this jumps up. So this represents the worst shock exposure. The fatigue creeps up dependent on the vibration exposure. So it's the fatigue damage which is adding and accumulating. And the idea of this is we want to create a statistical test which has at least the same fatigue damage and the same shock content as our target customer is going to see. So this allows us to create tailored tests which are much more statistically reliable, and we can use. And the nice thing with this is there are no standards for doing this for electric vehicles. So the best way to do it is to actually go and measure it and then to create our own tests to make sure that we're not going to get these battery failures. And these can include things like the torque cycles and the ripple effects and things like that. So when it comes to the mechanical and durability, just to sum up, then the first thing to realize is that batteries are effectively very complex mechanical systems. They're not just electrochemical systems, they're mechanical systems. They have lots of welds in there, lots of joints, and they're also resonant as well, with usually quite poor damping control. So again, we have to think about that. We're the experts at structural dynamics and fatigue. So, let's start to design those connections. So thousands of cells welded together, complex mounting constraints and variable damping. Of course, it's not just the structure. We need to understand the vibration environment. So there's a large range of excitation frequencies, really complex structure, a progressive failure. As I say, one cell doesn't mean the death of the battery, but it does mean a degradation in performance. So we need to be able to assess that impact on the durability, the reliability, the state of health of the battery. And finally, we're also interested in vehicle structures themselves. Making battery vehicles, and range is the priority. We want to make them as light as possible. We need to share platforms, for instance, with previous generations of thermal engines. But the new batteries have a completely different weight distribution. So how does that affect our structural durability? If we use batteries structurally to make stiffness, then how does those road loads impact the battery structure? And the general vehicle lightweighting itself. So if you went for a trip round our lab today, you wouldn't be seeing just metals being tested, but there's lots of tests going on of fatigue of joints. So welds, rivets, self-piercing rivets, adhesives going on, because lots of batteries contain adhesives. You'll also find fatigue of additive manufactured components. So additive manufacturing is a way of getting lighter, more durable components. And you also see fatigue of composites as well. So a lot going on vehicle lightweighting, again being driven by this need for electrification. As I say, I could talk about each of these for a long time, but I've got to get moving on. And I want to cover, before I go, the statistics and reliability side as well. So again, just want to cover three areas here. So first of all, battery life analysis. Then battery performance degradation. So how do we model the degradation of batteries over time? And also I want to talk to you about FMEA, failure modes and effects analysis, to investigate new failure modes. A really important aspect, I think. So the first thing to look at is that as engineers, there are two broad ways of doing design. They're rather grandly called the phenomenological approach or the constitutive approach. So the phenomenological approach is looking at failure in its entirety. It's building a statistics model, a bit like the SN curve. If you know stress as the input, you don't really mechanism, but you want to build a phenomenal model which gives you the statistics of failure. Now, a constitutive approach is the opposite. This is a physics-based model. So this is things like finite element analysis, kinematic analysis, doing fatigue and strain life curves and crack growth curves. But actually, when we look at it, most engineering design methods we use today are a mixture of both of these. So even though when we've done our fatigue, we've started off with big constitutive models, finite element with kinematic loads, we've done a fatigue analysis with rainflow cycle counting, our EN curve is actually a statistically derived one. So we tend to mix phenomenological and constitutive models. Now, if we're to have a look at, say, capacity loss on an electric battery, then capacity loss can be put down to either cycle life, so depth of discharge cycling, or calendar fade as well, so aging of the battery. And you can find this is just one extract that we caught from a paper. So if we look at these constitutives, we've got diffusion controlled reaction, kinetic controlled reaction, mixed diffusion kinetics, and for each of these we get this nice differential equation. But have you noticed that all these fitting parameters that are required, so we've got to develop a test to fit the equation, and there's a lot of these to do. So this is still an highly active part of research. But we can also tackle this using a phenomenological approach as well. So I'll talk about that in a second. Of course, capacity loss isn't the only failure mode. There's also mechanical failures, as we've seen. So battery pack failures, failures of the end tab welds, there's failures of the structure in the vehicle that can all be part of these failure modes. So we've got mechanical failures too. And of course, we've got auxiliary systems as well. So systems, if a cooling system fails, it won't necessarily kill the battery straight away, but it could lead to damage which is irreversible, which can shorten the life of the battery. So cooling and control systems are also really important. So you can see when we look at the battery, it's a very complex system, and a lot of it is still state-of-the-art research. So how do we go about building a reliable car when still a lot of the constitutive models are active research? So we need to bring them together. And a lot of this we can do today because we do have phenomenological models that can do it. So if all those equations are so complicated, how can we fit a statistical model through it? Well, a lot of these basically come down in the end to central limit theorem. So there are lots of inputs to it, but provided one doesn't dominate, then we tend to have a central limit theorem. And there are different statistical distributions which seem to fit different failure modes. So if we look at this, then the Arrhenius model is very good at looking at degradation with respect to temperature. The power law model, similar to what we use in fatigue, SN analysis and things, is very good at representing depth of discharge. And if we use things like the generalized area model, then this can be used to model both. But the aim of this is to try and work out, using technology that's available today, what's going to be our reliable life. So if I want to have a life of 8 years, that's my warranty period, how many components are likely to break in that time? You see, if I've got an 8-year warranty period, I don't want my mean time to failure to be 8 years, because 50% of those I've had to change on my dollar. And so we need to be able to represent not just the average, but the spread of those. Now, of course, these all require failures in a test lab. But thankfully, there are statistic ways that we don't have lots of them in order to get a good impression of what the mean and the shape of the distribution looks like. So my colleague, Dan Cruz, has been looking at quite a lot of these. And the first thing that we had to do is actually to define what is end of life. Because with fatigue, it's easy. It's parts in two, it's broken, that's the end of life. But what constitutes end of life for a battery? And a lot of people talk about the 80% life drop. And the reason why this is quite a good representation is because after that, we see the battery life drops off the edge of the cliff, really. So up to 80%, then that gives us the majority of the life. But then from comes rather quickly. So usually we talk about the 80% life drop as being the end of life. Now, there are many factors which could affect this. So temperature, depth of discharge, etc. So what's the important thing? In order to do this, if we want a battery that lasts 8 years, then we don't want to do lots of tests that take 8 years. So we need to accelerate those tests. So again, Dan, if you want to talk to him, has been doing work about looking at how we can accelerate tests. So if, for example, temperature has a big effect on life, then can we actually exaggerate the temperature and therefore make the test shorter, and depth of discharge and things the same? We can repeat them over and over again. So there are ways that we can accelerate those tests there. And Dan's done a Pareto analysis here. Now, this wasn't done on EV batteries. It was done on lithium-ion batteries, though, from mobile phones in this case. But we can see here the Pareto analysis is clearly showing the depth of discharge has the biggest impact on the endurance of the battery, the life, if you like, the charge capacity of it. The current's a secondary one here. and the state of charge and the voltage and the power, voltage times current. So again, we can start to see which are the key effects which are influencing the battery. And all of these have been done using technology that's available today. Now, when we look at that complex battery, we have to also consider that there are many different failure modes. And when we look at the reliability of a battery, we have to consider all of those acting together. So at the moment, we've looked a lot at the cell, for example, and we've said that in terms of failure modes, there's calendar aging and cycle aging are the key ones. But of course, we put lots of cells together and build modules. And then in the module, connector fatigue is quite common. And these have now got vibration and temperature cycling coming on here. So again, this can cause failure. And then when all the cells are assembled into a pack, we can then get structural fatigue of the pack. We can also get control problems and the thermal control and things of the pack too. And all of these things need combining. So this is where we use blocks in. So for example, at the cell model, then what we've got are two failure modes really, the cyclic capacity fade and the calendar fade. And we can build the probability models for each of those based on test. And in this case, they're parallel systems. So any failure in any one of those will lead to the cell effectively failing. Now, of course, the module is made up of about 30 or more cells. Now, all of these fit in parallel too. So one cell failing won't kill the whole module. So these are parallel. However, a connector fatigue could be a serial one. So when they fail in the connector, this is another mode. And of course, all the modules are then put together into a pack. So again, we can represent the failure of each of the modules, and we can combine that with a probability of the cooling system failing, for example. So now, based on all of these individual failure modes, we can bring those all together and we can start to look at reliability overall. So if we're designing a battery to last for 8 years, then what's my failure rate? Well, in this case, it's 20%. So that means if we put a warranty of 8 years on the battery, we would expect to replace 20 of them under warranty. So this is a really important calculation. It's one where we can build complex systems together just by joining their probabilities. But it also means we can look down and find out, so what's causing that? What's the primary failure mode? In this case, it appears to be a cooling system failure is the one that's most critically affecting. So again, we can know where to focus on how to make things better. So finally, I just want to have a look at FMEA. So FMEA is probably one of the things that's the easiest to fix today, and it requires no maths at all. So originally I wasn't very entertained by this because I like maths, but a lot of my colleagues prefer the management side of reliability. And this is probably, you get more bang from your buck for FMEA than pretty much anything else right now. So FMEA is failure modes and effects, and the FMEA is the criticality analysis. And really what it is it's a very structured and methodical approach to identifying and mitigating risk and warranty exposure. So the idea is we identify the potential failure modes, we assess the risk of those, we rank them all, and then we decide on what corrective actions to take. And the way we do that in this structured approach is, first of all, we take a component and we split it into all of its different constitutive items. And then for each of the items, we build a list of all the functions that that item has to be able to do. We then list all the failure modes. So these are modes that prevent the item from achieving that particular function. Then we list the effects, the consequences of those failures. And then we list all the possible root causes for those failures. So no maths in this, but already we've derived something that is extremely useful. We've derived a fault tree. And this fault tree can be used throughout the life of the vehicle, right down to the maintenance in the garages at the end, because it's linking consequence effects with root cause. So we can start to identify what the root cause might be. But again, FMEA goes a little bit higher. So now what we do is we can list all the current controls, all the strategies that are in place to improve the quality, to prevent these faults occurring. And we can list recommended actions of how can we make the reliability even better. And then for each of these, we calculate the risk priority number, the RPN. So the risk priority number is usually, we base it on three things and we rank each one between 0 and 10 and we multiply them together. So for example, there's a 0 to 10 scaling on the severity. So if this fails, how severe is it? If this were to fail, would the battery burst into flames and kill people? That's really severe. Or if a cell end tab came detached, then actually the battery would carry on, but it wouldn't have quite the same endurance. It would lose charge. That's less severe, still not wanted. But again, it allows us from a scale of 0 to 10 to rank these. Similarly, what's the likelihood of this occurring? And then what's the likelihood of us detecting it? Detection is important. Things like, what happens if your cooling system fails? How quickly can you detect this? Because that could be creating an accelerated damage scenario that you want to spot really quickly to stop. So by using FMEA, it enables us to do this and to produce really a list of all the different items, all the failure modes, and try and mitigate those today. Gone out. And the nice thing about this is it really works well for novel and new structures where we don't have lots of expertise and experience already. So typical to EV batteries, really. Now, with my experience of FMEA, there's a few things that I've sort of pulled out from talking to customers. So the biggest thing here is don't use Excel. The power of FMEA isn't in filling in a sheet. The power of FMEA is in its ability to capture knowledge and recycle that knowledge later. So Excel just means you're ticking a box, but it's never reused. True FMEA needs to capture that knowledge so that you can reuse it. The other thing is don't leave it to the reliability engineer. There is more knowledge in a team than in an individual. And throughout your team, if you get people together, so the reliability engineer is the host, the chairman of the meeting, we can get all of that knowledge out of people's heads into the FMEA, so that now becomes corporate knowledge and can be reused. Another thing is, each of these items or systems are reusable. So as we develop new batteries, we can pick the FMEA from the database of things we've used before. So that enables us to assemble complex things very quickly. So it saves a lot of time. And it means that we can share this database as well throughout the company. Also, the database isn't just for the early stages. We can actually expand it. So when we start to get failure modes, say, coming back from maintenance, we can use FRACAS, Failure Recording and Corrective Action System, to start to update the FMEA based on the warranty data we're getting. And similarly, we can link it with numerical analysis. So as we start to do tests, as we start to do the lab tests, we can take that life data analysis, that reliability centered maintenance, and this can all feed in to our make it really a central repository of domain knowledge within the organization. So FMEA is actually the start to something much bigger. So in conclusion then, for statistics and reliability, we've looked at battery life analysis, and this is using technology available today to build that phenomenological model so that we can start to estimate the B10 life, etc., look at reliability life estimates, and look at planning for maintenance. Of course, we're also interested in modeling battery performance at that constitutive level as well. So by building these models, we can start to look and investigate what is electrochemical degradation, how does it compare with others. We can start to combine lab tests with real-world data. We can develop data characterization models and statistical battery models. So again, this is a way that our knowledge will grow. And then finally, through FMEA, batteries are really complex and they have some novel failure modes. FMEA will enable us to spot those early so that hopefully we can reduce the impact of failures in production. And FMEA can be applied both at the system, in the design stage, the manufacturing process to improve overall quality. So in conclusion then, we've looked at these three areas. We've looked at performance, at durability, and reliability. And in that performance, we're all about getting better range, better accuracy, and understanding the customer usage. In that mechanical and durability area, it's all about realizing that batteries are mechanical structures, and we can reduce battery degradation by improving the structural durability. We also need to understand what vibration loads they're going to see in practice, and we need to produce better tests for those. And also, don't forget that as we're trying to make vehicles lighter, we're trying to represent those failure modes too, so lighter, more durable vehicles. And then finally, on the statistics and reliability, we want to reduce warranty exposure with the technology and knowledge we have today, first of all. But then we want to use it as our knowledge improves. We need to understand and reduce the degradation further with those constitutive models. And finally, with FMEA, this is really good for novel structures like the batteries. It reduces the risks, and that means we can build brand image and we can build knowledge as well, which can be reused later on.